Hey students, we've made it to the last lecture in this module. It's going to be about, well, I say on the first slide it's going to be about clouds and precipitation, but let me tell you what, I actually had a change of heart about that. I was thinking about it and I was like, why would we talk about precipitation in this module? Precipitation doesn't have a particularly interesting impact on either electrical load or yield. Unless I suppose if you wanted to talk about like hydroelectric power, for example, where, you would need the runoff and things like that, but that's fairly far from the kinds of things we're going to be doing from this course. So let's just kind of pretend we crossed out the words and precipitation and just talk for a little bit about clouds. And of course, clouds very directly affect the electrical yield of things like solar panels and so on. And they also, they do it in a number of different ways actually. They keep some solar radiation from reaching the surface by reflecting it back into space. That's lost energy. That is energy that was headed towards the Earth but never made it to the surface where your solar cells are, and instead was reflected back off into space. So unless you have some plans to do something like on the International Space Station where you're going to have these big solar collectors, any kind of ground-based solar array is going to have a problem with lost energy due to clouds. Clouds also absorb some of the radiation, some of the sunlight, reducing what is available to solar power production. That's a little bit more complicated, they more scatter it and so on, but it is true that some of the radiation is lost before it is able to reach the solar panel and be converted into electricity. And I have this little interesting set of diagrams here. These diagrams over here are showing you some data that was collected at a field site. I would want to draw your attention here to the third row down here. I drew a red box around it so you can see these are just data that are being collected from a radiometer that is measuring solar radiation, and inside of that red box there is just measuring 1 day's worth of data as it goes from left to right. And you can see how at first the amount of solar radiation was 0, and then it formed this kind of nice mound as it had a peak around noon, and then during the course of the day the amount of solar radiation decreased until it hit sunset, and then the amount of solar radiation shortwave down was 0 again. That's a perfectly clear day there that I have circled in, with a box around it in red. It is showing the amount of solar radiation that is received on a clear day. And if I just illustrate it with this blue box here, that's another day in which there was some cloud cover, and you can see how the solar radiation that is observed at any given time is not necessarily the amount that was observed at that same hour on the clear day, and that's because some of the times there were clouds that were attenuating the amount of radiation that was reaching the surface where the radiometer was at that time. We're actually going to come back and look at more diagrams like this in just a little bit. Partly cloudy conditions actually are really complicated situations with regard to the shortwave flux at the surface, whether we're talking in meteorology about warming the ground, or whether we're talking in this context of like energy yield, where we're talking about the amount of power that's produced by a solar panel. So partly cloudy conditions result in highly variable amounts of solar radiation that can reach the surface. This is because the clouds themselves block some radiation, but the sides of the clouds are extremely reflective. So if there isn't a cloud directly above you, between the solar panel, say, and the sun, and there are other clouds around it, not only are you getting direct radiation transmitted right from the sun to your solar panel, but you're getting radiation that's reflected off of the sides of the clouds around you. And so I found this example here that is actually a nifty example of the kind of thing I'm talking about here. So this is 1 day's data collected at a radiometer. It happens to be on a partly cloudy day, and in that thick red line I'm showing you approximately where the curve would be as to how much solar radiation we would be receiving if the location were clear. There were no clouds on that day. I don't have it quite a perfect fit. It's hard to do that on PowerPoint and get a good fit, but that's approximately what the radiation curve would look like over the course of the day if it were perfectly clear. And you'll see that there's plenty of times where we're getting much less energy than that, and that's because there was a cloud between the radiometer and the sun, and so the amount of radiation was attenuated. But notice that there are some spikes above the curve as well. Times where we were actually getting more shortwave radiation than we would have gotten if it had been perfectly clear. And that's because those are situations in which there were no clouds between the radiometer and the sun. The sun's rays were falling directly on the radiometer, and other clouds in the area were reflecting sunlight onto the radiometer as well. So we got these very high amounts of radiation at a few times along the way. This is, by the way, part of the reason why you get a sunburn more on partly cloudy days than you do on a cloudy day. I mean on a clear day rather, and it's because the clouds, you can get these spikes of very high amounts of radiation. The truth of the matter is your body is actually fairly well designed to deal with the amount of radiation that you would receive from the sun under clear conditions. It's these spikes where your body is not designed to take these very high fluxes of solar radiation that happen under partly cloudy conditions. Your solar panels would need to be able to take them too, of course. So there's times when the power received was less than what we would have seen under clear conditions, but strangely there were times when the power received is actually more than what you would see under clear conditions, due to reflection of sunlight off the sides of the clouds. Clouds also affect electrical load in all kinds of interesting ways, mostly by affecting the temperature at the surface. For example, if I take a look again at one of these kind of diagrams here, where I'm showing you two different days, there's 4 days of data here, but I'm interested only in the one that I have drawn in red and in the other one in blue with the blue box. On that red box there, you can see how we have a day where it's perfectly clear. The solar flux at the surface just follows that little hump-shaped distribution. No radiation until sunrise. Then the shortwave down just follows a nice hump-shaped peak, peaking at noon, and then lowering until sunset in the evening. And if you look at the top there, that is just the air temperature at that location, and you can see how the sun, after sunrise, the temperature just went up all day until almost at sunset, and then the temperature started falling. A pretty straightforward idea of what you think the temperature should do over the course of a day. But now check out what happened in that day that I have highlighted in blue. That was a day when it was there were clouds, and you can see how the distribution of sunlight over the course of the day was very strange. At first we had no sunlight until, no shortwave down until the sun came up, and there was some amount of shortwave down increased for a while, but then there were all these times when it was quite suppressed because of the clouds. And there was some times in late afternoon when the solar radiation was fairly large, but by the evening, of course, the amount of solar radiation was decreasing and then finally came to zero at sunset. Now, follow the arrows up to the air temperature curve at the same time that I also have highlighted in a blue box. Look how the air temperature never really increased all that much during that course of that day. Yeah, the temperature did increase, but clearly nowhere as much as it did on a day where it was clear. The amount of shortwave radiation was greatly modified by the clouds, and therefore the air temperature didn't change as much. And you would have the same sorts of thought then about well, how would that affect electrical load? I mean, you wouldn't necessarily need as much air conditioning, for example, under those kinds of conditions as you would have needed if it had been completely sunny. I think you're pretty sold on this idea then that clouds are important for a class like electrical load and yield, and you can well imagine that we're going to be talking about the distribution of clouds in all kinds of interesting statistical ways over the course of the semester. All clouds, just to talk about the mechanics of how they form, are formed by rising motions in the atmosphere. That's a good thing to keep in mind when you're trying to think through like any given weather situation. Clouds are always formed by rising motions. See, as a volume of air rises, it's always encountering lower pressure. Remember, pressure always decreases as you go up in the atmosphere. So as air parcels rise, they have to be experiencing lower pressure. Well, the air parcel, as it encounters lower pressure, expands. But expanding, as you experience lower pressure, is work. I mean, picture like a balloon as it rises. As it rises, it encounters lower and lower pressure, but as it does so, it's also expanding, which means it's also doing work, pushing other air out of the way. Doing work in this way means that the temperature of the air parcel falls, and as the air parcel's temperature decreases, the saturation vapor pressure, which also depends on temperature, decreases as well. Remember, saturation vapor pressure was just a measure of the amount of water vapor that volume of air could be holding. That depends on the temperature. So if the temperature is falling, the amount of water vapor the air parcel could be holding is falling as well. The amount of water vapor in the air isn't changing. Vapor pressure stays the same, but saturation vapor pressure decreases. And since relative humidity is just vapor pressure divided by saturation vapor pressure, relative humidity increases. We're getting closer and closer to saturation to remember what relative humidity really means. Relative humidity being just a measure of how close you are to saturation. So at some point, as we lift this air parcel, we'll actually hit a point where the air becomes saturated, and then from then on out, we'll be condensing water vapor into little liquid water droplets. So vertical motion is key to the formation of any type of cloud. And as it happens, there's a number of ways in the atmosphere we can get vertical motion. In fact, if we just steal some ideas from an intro textbook, we could say that there are 4 ways to produce vertical motion in the atmosphere. One we've actually talked about in some length already. Remember this slide that we had back when we were talking about winds? We talked about there were cyclones and anticyclones at the surface, areas of low pressure or cyclones, areas of high pressure or anticyclones. And they had winds spiraling either clockwise or counterclockwise around them, but they also spiraled into the center of the area of low pressure, the cyclone, and made convergence and rising motion. And the anticyclone had air spiraling out of the center of it and large-scale sinking motion to replace that air. So cyclones have areas of convergence at the surface, and there's no place for the air to go except up. We can generalize that and just say that one way in which we can get vertical motions in the atmosphere is through low-level convergence. There's actually lots of different ways to get air to converge at the surface. Sea breezes converge at the surface. Air converges at the center of hurricanes. Air converges at lots of reasons at the surface. Okay, a meteorology major could talk about all kinds of different ways you can get convergence at the surface, but anytime you get air at the surface to come together, there's no place for the air to go but up. It can't go down into the ground. Another way in which we could get air parcels to rise and produce clouds would be to force them over mountains. Like here I have a picture that I found on the internet that's got the wind blowing up this slope of the mountain, the way those green arrows are showing, and you can see how we're getting clouds forming as that air has been lifted to a certain height up the side of the mountain. And that gives us a sense that a second way in which we could get vertical motions in the atmosphere would be through lifting as the air goes over a mountain. The fancy schmancy word we use in atmospheric sciences for that is orographic lifting. Orography is a fancy word for like mountains. Another way in which we could get vertical motions in the atmosphere and therefore clouds has to do with the meteorology of situations when there's a front. Now we're not going to talk about the meteorology of fronts at this time. But this is a good example here of a diagram of a cross-section of a front, where a warm air mass coming from the south is meeting a cold air mass coming from the north. These volumes of air the warm, light air tries to ride up over the top of the colder, denser air, and that rising motion as the warm air slips over the top of the cold air mass produces a type of rising motion that has the terribly silly name of frontal wedging. Okay, it has to do with the fact that there's sort of a wedge shape to this whole thing. I always think that frontal wedging is about the silliest word ever. It sounds like something little kids do to each other in the playground or something. They give each other frontal wedgies or something. Frontal wedging is the right technical glossary of meteorology term for this situation. And finally, our fourth way of getting vertical motion in the Earth's atmosphere is illustrated beautifully in this scene right here. Here we have a beautiful open field where there's air touching the warm ground on a sunny day. The air warms by conduction. It's always warmer and lighter than the air around it, and it rises in just these beautiful little buoyant plumes. Way number 4 to get rising motion in the atmosphere is just buoyancy. When a volume of air is warmer and lighter than the air around it, it rises. Another word for that, by the way, is convection, just to throw us all the way back to that lecture about ways to move heat around in the atmosphere. Here we're moving heat by moving air parcels vertically. So we have all these different ways to get rising motion, and the result is a couple of different types of clouds. Now there's a lot of different ways in different meteorology textbooks to kind of sort the clouds out by into different types. I mean, they're all going to stick with the same names, but they're going to group them slightly differently. But I like to think about them in terms of their function and how they form. There's a whole cluster, there's a whole type of clouds out there that go under the name cumuliform cloud. Cumuliform comes from a Latin word that means something like heaping or piled up or something like that. And these are always clouds that are formed by buoyancy. A good word for these types of clouds is that they are active clouds. These are clouds that are forming because this air inside the cloud is warmer than the air around it. The air inside the cloud is warmer than the air outside the cloud. The air, therefore, is buoyant, it wants to rise, and as it rises, it continues to produce cloud. And so you get these clouds that, once you know that these kind of cumuliform clouds are formed by rising air parcels, well, once you start looking at it, this guy you can kind of even see how it's this rising motion and all these little towers and so on. A good example of a cumuliform cloud are the cumulus clouds, the little puffy clouds that you see in fair weather conditions on a summer day. Another example of cumuliform clouds are cumulus congestus or thunderheads. These are like the early stages in the life of a thunderstorm. For that matter, thunderstorms themselves, cumulonimbus clouds, are brilliant examples of a cumuliform cloud. They are active clouds. They are formed because the air particle is actually buoyant and warm compared to the air around it, and it is rising on its own. This is in contrast to a more passive type of cloud called stratiform cloud. Stratiform clouds are produced by mechanisms other than buoyancy. Like all clouds are formed by rising motion, but they're not being formed because there's some dynamic situation here that is causing this air to be warmer than the air around it and buoyant and it's rising on its own. Something is forcing the air to rise if we're talking about a stratiform cloud. And so we use this word passive cloud. The air is not doing the work to be lifted, it's being forced to rise by like maybe convergence, or maybe it's due to frontal wedging, or the air is being forced to rise over a mountain. The air is not rising on its own, it's being forced to rise. There's lots of types of stratiform clouds, like stratus. They're just sort of these broad areas of overcast conditions. Altostratus, that's when the sky is sort of that whitish gray color, and you can kind of see the sun through it. They're not particularly thick. We'll talk about their role in energy production and so on in a little bit, but there is one other type of cloud I want to get to first, and that's these cirriform cloud. Cirriform cloud, is a word that comes from Latin again, and it means something like fibrous or threaded or something like that. And cirriform clouds often have that kind of mare's tail, like a horse's tail, look to it. They have kind of long filaments. They're not actually there. That's just how they look. They're actually made up of little ice crystals in the atmosphere. They're not literally like long strings in the air or something like that, but the people who came up with the name for them about 210 years ago didn't know that cirriform made a perfectly good sense. They're thin, they're wispy clouds, they're made of ice, and they are a type of passive cloud as well. They are very high up in the atmosphere. Examples of them would be like these cirrus clouds. I mean, look how thin and wispy and kind of filamented they look. Again, that's just ice crystals falling that makes that appearance there. But they are cirriform clouds. Here's some cirrostratus clouds. Those are layers of thin, wispy clouds made up completely of ice. All these different clouds, of course, can have effects on solar power. The cumuliform clouds tend to make the amount of solar power that is produced by a solar collector very highly variable with respect to time. As a cloud passes between the solar panel and the sun, you'll have this big dip in the amount of power you're producing, and but then the cloud is passed and you'll have a very big spike in the amount of power and so on. The overall production over the course of a day will typically be quite low if there's cumuliform clouds in the area. There may be moments where there's spikes of large amounts of power, but overall the total production is going to be quite low. Stratiform clouds also result in a relatively low amount of power at the surface. Most of the radiation that will be reaching the surface when there's stratiform clouds, in other words when the sky is overcast, will be this very diffuse radiation that's been scattered through the clouds. It's not any longer coming in the direction of the sun, it's coming from all angles. And it's difficult to know how to position a solar panel to best take advantage of that, etc. Your overall production of power will be relatively low under stratiform clouds. Cirriform clouds themselves actually have relatively little effect on solar power production, as most solar radiation is transmitted through a cirriform cloud layer, although some will be reflected or absorbed by those ice crystals, so you will have a diminishment of the overall amount of power collected, but cirriform clouds certainly have the smallest effect of all of these. Okay, that's the end of the last lecture that makes up Module 1 in this class. Check as to what happens on the next part of this module to kind of review as to how we're going to move forward now. Alright, please let me know if you have any questions. This has been Dr. John Schrocki.